All right, welcome pre-calculus students. Sorry that I am gone again 2 days in a row. That's never good. Yesterday I had a meeting at Washington Township for the afternoon, and then my youngest daughter Jenna got sick, and so I am home with her today, unfortunately. Talking about complex numbers here. To get started, we just want to make sure that we can add and subtract polynomials and multiply polynomials, because those are the same things that we do with complex numbers, and treating them a lot of times like the variable x. So go ahead and push pause and add and subtract, multiply these polynomials and see what you get. Share them with someone around you. All right, here come the answers. I see that they came in a little bit funny with notation, but I think you can see what each of them turns out to be. Hopefully you got the same thing on each of them. Talking today about doing operations with complex numbers, and that's stuff that's very much review from advanced algebra. Maybe talking a little bit more about conjugates, which is again not a new word, a word you heard in advanced algebra, but maybe something we need some reminder of. What do you remember about complex numbers? Most of you will remember that a complex number is the number I, and that I is the square root of -1. And then the other super duper important thing that I'm guessing you do remember from advanced algebra, that if I is the square root of -1, then I squared, imagine squaring both sides of that, would be -1. And so that's going to be another important thing that we need to remember. So leaving an I squared in your answer is not an option because it's not simplified. I squared simplifies down to -1. This is what a complex number looks like. It has a real part and an imaginary part. The real part is considered A, the part without an I, and the imaginary part is considered B, the part that is multiplied by the I. So a complex number in standard form looks like A plus BI. With those complex numbers, you can add them together by adding the real parts and adding the imaginary parts. Same thing with subtraction. So the difference of complex numbers, you subtract the real parts and you subtract the complex part. The imaginary part. Here's some practice, just doing different operations with these. Let's do a few of them together. The first one says 3i plus I. Well, 3i plus I means 3i plus 1i, which would leave us with 4i. The next one is -1 minus 8i minus 4 minus I. So if I group together my real parts, that'd be the -1 and the -4. That leaves me with -5. And I group together the imaginary parts, -8i and -I. That leaves me with -9i. So in standard form, I get -5 minus 9i. And I'll do this third one and let you work on the bottom too. So I would probably start this one by distributing that negative. So I have -3 plus 6i plus 5 plus 3i minus 8i. And then again, grouping like terms. Let's see, I have a -3 and a 5. Those put together to be 2. And I have a 6i, a 3i, and a -8i. And let's see, 6 plus 3, that's 9. 9 minus 8 is 1. So 2 plus I, if I did my math right, there is my answer for that one. Go ahead and push pause and work on those bottom two and see what you think. Share them with someone around you. All right, now we are getting to multiplying more of these complex numbers, and you multiply by distributing, or some of you think of the acronym FOIL when you're multiplying these. So if I do that with this first one up here, I need to take 2 times -6, which is -12, and then I take 2 times 4i, which is 8i. Then I distribute the -4i times the -6. 2 negatives make a positive, so plus 24i. and negative 4i times positive 4i. That's negative 16i squared. All right, so grouping like terms here in the middle, that leaves me with negative 12 plus 32i. And this negative 16i squared. I squared we said was negative 1. So this is negative 16 times negative 1, which is plus 16. And then grouping those like terms together, my final answer is 4 plus 32i. Go ahead and push pause and work on that second one. All right, working on this third one here. First, I would maybe distribute the 6 to that first term right there. I don't distribute the 6 to both sets of parentheses because you do not distribute multiplication over multiplication. You only distribute multiplication over addition. So I'm distributing that 6 to that first set, and I get negative 42 plus 36i. And then that needs to be multiplied by the negative 4 plus 2i. And you can multiply that out and simplify. But since I'm in a hurry, I'm going to go on, move to the next one. But know that this one is not finished yet either. On the bottom one, I have 5i plus 7i times I. Well, I times I is I squared, so I have 7i squared. But I squared we know is negative 1, so this becomes 7 times negative 1, which is negative 7. And in standard form, my final answer is negative 7 plus 5i. How about that? I would like you to try this one right here. 1 minus 7i, the quantity squared. And this one right here, 6i to the third power. We'll touch base with those on Wednesday when I come back. All right, so get into this word conjugate. This is a complex conjugate. The notation for a complex conjugate is this bar above it. That's new notation most likely, something you haven't seen before. And so this is saying that the conjugate of a plus b is a minus bi. So the conjugate of a plus bi is a minus bi. Notice the real part stays the same, a and a. What changes is the imaginary part. It went from b to negative b. So the number is staying very much the same. The only thing that is changing is the imaginary part changes from a positive to a negative or a negative to a positive. The nice thing about conjugates is when you multiply them, it becomes a real number. And that's the reason why complex conjugates are so nice, is because you can take this complex number, multiply it by its conjugate, and now it's no longer complex. It's in the real number system. This is talking about multiplicative inverses of conjugates, and I will talk about this when I come back. But if I want to write a number in standard form, I need to get the complex number out of the denominator. I'm going to do one example of these and call it quits for the day. So to do that, on this very top one right here, 3 over 5 minus I, our strategy is to multiply by the complex conjugate of the denominator. So the complex conjugate of 5 minus, oh, where's my eraser? Oh, don't do that. All right, you're going to have to live with that dot there because I don't know how to get it off there. All right, so the complex conjugate of 5 minus I is 5 plus I. If I'm multiplying by 5 plus I over 5 plus I, it's like multiplying by 1. So I'm not changing the meaning of the number at all. It's just multiplying by 1. And in the numerator, I can distribute. So I take 3 times 5, which is 15, and 3 times I, which is 3I. There's my numerator. In the denominator, I have to distribute as well, but this time it looks more like FOIL. So I take 5 times 5, which is 25, My outside term is 5i. My inside term is negative 5i. And my last term is a negative I squared. Here's the beauty of complex conjugates. I multiplied those together, and my inside terms, that 5i and negative 5i, go away. I'm left with 15 plus 3i over 25 minus a negative 1. I'm left with a real number on the denominator. I have 15 plus 3i over 26. My 7-year-old and 9-year-old with me can hardly contain their excitement about this awesome math stuff. Now, to put my answer in standard form, I give that denominator to both pieces of the numerator. So final answer, 15 over 26 plus 3 over 26 times I. And there is your answer in standard form. Pretty cool, huh? Glad I'm not there to hear your answer because I fear that it would not be as cool as I think it is. The reason we talk about imaginary numbers is because they come up when we are solving equations like the quadratic equation. We have a square root in there. So oftentimes when we take that square root, or sometimes I should say, there's a negative under that square root. If there's a positive number under the square root, then we have real numbers and everything's good. We have plus or minus whatever that real number is. If there's a 0 under that square root, then we have only one solution because it's plus or minus 0, so there's one real solution. And if that underneath the square root, b squared minus 4ac is negative, that's where this complex number comes up. So since that b squared minus 4ac is discriminating between what type of solutions it is, that is why we call that the discriminant. So b squared minus 4ac, it's called the discriminant, and it tells me whether my solutions are going to be real or complex. It tells me whether there's going to be 2 or there's going to be 1, the discriminant. Here's an equation. I want you to solve it using the quadratic formula. When you do that, you're going to get a negative number underneath the square root. Simplify that out. We can't leave negatives underneath the square root, so we're going to write it as I, and you're going to have your answer as a complex number. Go ahead and push pause and solve that. Hopefully you ended up with this number right here, negative 2/3 plus the square root of 11 over 3 times I. It would also be okay to write your answer like this, negative 4 plus or minus I times the square root of 44 all over 6, and then put it in standard form from there. So give that 6 to both pieces of the numerator if we needed to, but this answer right here is good too if you don't simplify your root. Here's a chance for a couple more practice. Why don't you pick 1 or 2 of them to do with the person next to you and see what you get. I go, here's your homework. I hope you are having a chance to take a look at some of this stuff, and I will catch you up on what I can tomorrow. Hope you guys have a great day.